This module of Chapter 5 on population, Module 5.3, I give background to stable population theory and derive the classic model referred to as the Lotka Equation. Background. One of the largest singular achievements in demography was the linkage of stable theory to real populations by Lotka in 1907 and 1928 publications. Lotka originated the terms and the concepts of a stable age distribution, SAD, and the intrinsic rate of population growth, R, and noted that a population growing with fixed birth and death rates will eventually evolve to the state where growth rate is constant and the fraction of the total population in each age class is fixed. This integral equation is now known in demography as the Euler Equation, after the French mathematician, the Lotka Equation, after Lotka, or the characteristic equation, and it serves as the foundation of virtually all renewal theory in biology. The stable population model derived by Lotka in 1907 thus provided both a conceptual and an analytical tool for demographic analysis of populations. His model provides the foundation upon which virtually all population models are built. Uses and assumptions of the model. The objective of the stable model is to trace the dynamic characteristics of a population that start off with an arbitrary age structure and is submitted from that moment on to a specified demographic regime. The most important conclusions of this theory are twofold. First, that the age distribution of a population is completely determined by the history of fertility and mortality rates. Second, that the particular schedule of birth and death rates set forces in motion that makes the age structure and the rate of population growth tend towards an inherent steady state that is independent of initial conditions. The assumptions of the stable model are basically the same as those of the crude rate model, except that age structure is incorporated into a stable model. Like the crude rate model, the stable model assumes, first, fixed birth and death rates, second, a closed population, that is, no migration, and third, one sex. These assumptions highlight some of the limitations of the applicability of the theory to natural populations. However, when used properly, stable population models provide starting points for addressing fundamental questions about processes of population renewal. They identify the two most important population parameters, that is, age distribution and growth rate, their interdependence, and their relationship with the cohort parameters of birth and death. Suggest a direction for population growth, the sign of population growth, and the general skew of the age distribution, and they can project actual numbers that may be useful as frames of reference and also for asking what-if questions. Derivation. Consider the simplest age-structured population model consisting of three age classes. The number at age 0 at time t plus 1 equal the reproduction at age 1, which is m1, times the number age 1 at time t plus reproduction at age 2 times the number at age 2 at time t. Next equation, that would be that the number in age class 1 at time t plus 1 equal the probability of surviving from 0 to 1, that is p naught, times the number of newborn, that is at age 0 at time t, and then the number at in age class 2 at time t plus 1 will be the probability of surviving from 1 to 2 times the number in age class 1 at time t, where nx at time t and nx at time t plus 1 denote the number of individuals in the population or age x at times t and t plus 1. Mx denotes the number of offspring produced by a female age x, and px is the probability of surviving from age x to age x plus 1. The objective is to find the rate at which this population will increase each time step. That is to say, the finite rate of increase lambda. Since the rate at which population increases also applies to the rate at which the number in each age class increases, we set the ratio of the number in each age class at time t plus 1 to the number in each age class at time t. The ratios of the numbers in the population age x at times t plus 1 and time t are set equal to lambda. Then each can be re-expressed as the numbers at age x and time t plus 1 equal the products of lambda and the numbers age x at time t. These equations state that the three age classes 0, 1, and 2 increase each time step by a factor of lambda. Substituting the right-hand sides of these equations yields this new set of equations which, with further resubstitutions, which I don't cover here, but in the book we do, yields the three age class version of the Lotka equation. By setting lambda equal e raised to the r, where r denotes the intrinsic rate of increase, gives the discrete version of the classic Lotka convolution renewal equation as 1 equal the sum of the product of e raised to the minus rx times lx mx, where alpha and beta are the first and last ages of reproduction, respectively. The value of the intrinsic rate of increase r is determined using numerical methods as described in the next module. This Lotka model serves as the analytical and conceptual foundation for essentially all of population renewal theory. This ends Module 5.3.